We now look at optical rotary encoders. An optical rotary encoder produces angular position data directly in digital form, eliminating any need for the ADC converter. The concept is illustrated and shows a slotted dark disk attached to a shaft. A light source and the photocell arrangement are mounted so that the slots pass the light beam as the disk rotates. The angle of the shaft is deduced from the output of the photocell. There are two types of optical rotary encoders, the absolute encoder and the incremental encoder. And now we'll look at both of these. The absolute optical encoders use a glass disc marked off with a pattern of concentric tracts. A separate light beam is sent through each track to individual photosensors. Each photosensor contributes 1 bit to the output digital word. The encoder shown outputs a 4-bit word with the least significant bit coming from the outer track. The disk is divided into 16 sectors, so the resolution in this case is 360 degrees divided by 16, which is 22.5 degrees. For better resolution, more tracks would be required. For example, 8 tracks providing 256 states yields 1,4 degrees per state, and 10 tracks providing 1,024 states yields 0,35 degrees per state. An advantage of this type of encoder is that the output is in straightforward digital form and, like a pot, always gives the absolute position. This is in contrast to the incremental encoder that, as will be shown, provides only a relative position. A disadvantage of the absolute encoder is that it is relatively expensive because it requires that many photocells be mounted and aligned very precisely. If the absolute optical encoder is not properly aligned, it may occasionally report completely erroneous data. Figure 6.10 illustrates this situation, and it occurs when more than 1 bit changes at a time, say from sector 7, which is 0111, to 81000. In the figure, the photosensors are not exactly in a straight line. In this case, sensor B1 is out of alignment. It's a head, and it switches from 1 to 0 before the others. This causes a momentary erroneous output of 5, which is 0101. And if the computer requests data during this transition time, it would get the wrong answer. One solution is to use the gray code on the disk instead of the straight binary code, which is shown in figure 6.11. When the gray code is used, only 1 bit changes between any 2 sectors. Have a look at this yourself. Just go from number to number, seeing that there's never a change of more than 1 bit. If the photocells are out of line, the worst that could happen is the output would switch early or late. Put another way, the error can never be more than the value of the least significant bit when using the gray code. The incremental optical encoder has only 1 track of equally spaced slots. Position is determined by counting the number of slots that pass by a photosensor, where each slot represents a known angle. This system requires an initial reference point, which may come from a second sensor on an inner track, or simply from a mechanical stop or limit switch. In many applications, the shaft being monitored will be cycling back and forth, stopping at various angles. To keep track of the position, the controller must know which direction the disk is turning, as well as the number of slots passed. A single photosensor cannot convey which direction the disk is rotating. However, a clever system using 2 sensors can. As shown, the two sensors, V1 and V2, are located slightly apart from each other on the same track. For this example, V1 is initially off, well, almost, you can see it's half covered up, and V2 is on. Now, imagine that the disk starts to rotate counterclockwise, or CCW. The first thing that happens is that V1 comes completely on, while V2 remains on. After more rotation, V2 goes off, and slightly later, V1 goes off again. Figure 6,13b shows the waveform V1 and V2. Now, consider what happens when the disk is rotated in the clockwise direction, starting again from the position shown in figure A. This time V1 goes off immediately and V2 stays on for half a slot and then goes off. Later V1 comes on, followed by V2 coming on. Figure C shows the waveform is generated by V1 and V2. Compare the two sets of waveforms. Notice that in the CCW or counterclockwise case, V2 leads V1 by 90 degrees, whereas for the clockwise case, V1 is leading V2 by 90 degrees. This difference in phase determines which direction the disk is turning. The hardware of the incremental encoder is simpler than for the absolute type. The price paid for that simplicity is that we do not get direct binary position information from V1 and V2. Instead, a decoder circuit must be employed to convert the signals from the photosensors into a binary word. Actually, the circuit has two parts. The first part extracts direction information, and the second part is an up-down counter which maintains the slot count. The block diagram shows this. V1 and V2 are converted into new signals denoted by count down and count up. The count down signal gives one pulse for every slot passed when the disk is going counterclockwise. The count up signal gives one pulse for each slot when the disk is rotating clockwise. These signals are then fed to an up-down counter, such as the TTL 74193. This counter starts out at 0, and it is usually reset by the reference sensor, and then proceeds to maintain the position by keeping track of the counterclockwise and clockwise counts. Linear variable differential transformers. Simpler than the name suggests. The linear variable differential transformer, or LVDT, is a high-resolution position sensor that outputs an AC voltage with a magnitude proportional to the linear position. It has a relatively short range of about 2 inches, but it has the advantage of no sliding contacts. Figure A illustrates that the unit consists of 3 windings and a movable iron core. The center winding, or primary, is connected to an AC reference voltage. The outer 2 windings, called secondaries, are wired to be out of phase with each other and are connected in series. If the iron core is exactly in the center, the voltage induced on the secondaries by the primary will be equal and opposite, giving a net output, V net, of 0 volts, as is shown in figure C. Consider what happens when the core is moved a little to the right. Now there is more coupling to the secondary 2, so its voltage is higher, while secondary 1 is lower. Figure D illustrates the waveforms of this situation. The algebraic sum of the 2 secondaries is in phase with secondary 2, and the magnitude is proportional to the distance the core is off center. If the core is moved a little left of center, then secondary 1 has the greater voltage, producing a net output that is in phase with the secondary 1, figure B. In fact, the only way we can tell from the output which direction the core moved is by the phase. Summarizing, the output of the LVDT is an AC voltage with magnitude and a phase angle. The magnitude represents the distance that the core is off center, and the phase angle represents the direction of the core, left or right. An oscillator provides the AC reference voltage to the primary, typically 50 to 10 kHz at 10 volts or less. The output of the LVDT goes first to a phase-sensitive rectifier. This circuit compares the phase of the LVDT output with the reference voltage. If they are in phase, the rectifier outputs only the positive part of the signal. If they are out of phase, the rectifier outputs only the negative parts. Next, a low-pass filter smooths out the rectified signal to produce DC. Finally, an amplifier adjusts the gain to the desired level. The output of the LVDT interface circuit is a DC voltage whose magnitude and polarity are proportional to the linear distance that the core is offset from the center. Some integrated circuits, such as the 8698, combine all the functions shown within the box on a single chip. This ends our brief review of position sensors.